In the previous video, we looked at a pendulum. So the length of the string is L. The time it takes to make one swing is given by T, and G here is gravity. Now, in the previous video, we kept the gravity the same, and we varied the length of the string, and we came to the conclusion that the time it takes to do one swing is proportional to the square root of the length of the string. Now, in this video, we're going to keep the length the same, but we're going to vary gravity. So what would happen if gravity were to double were to double or were to times by 3? What effect would that have on the time it takes to make one swing? So if we were to double the gravity, what effect would that have on the time it takes to make one swing? Okay, so start with this formula here. Okay, so now remember we are keeping the length of the string the same. So again, we're going to use this property where if you have a square root of a over b, that equals root a over root b. Now, if you don't understand this, watch the indices section. Okay, so from here we're going to jump to here, 2 pi times root L over root G. Remember, we're keeping the length of the string the same. We are varying G, okay, gravity. So here you've got this this bubble here multiplying a fraction, so it will get multiplied to the top. So this will be equals 2 pi root L over root G. Okay. So now hang on. Yeah, so now visualize it like this. All this here is stuck in a bubble here. So let's take this out. So it will be like this. 2 pi times root L. Remember, root L, we don't really care about the length of the string. We're keeping the length of the string the same. So that times 1 over square root of G. Okay, so you've got this thing here. So if we were to work backwards, here you've got a bubble multiplying a fraction, so it will get multiplied to the top, taking you back to here. So what I'm trying to say is, if you're here, you can jump to here. Okay, so here, so you're here now. So you're here at the moment. You see, this thing here is just a number that we don't care about. Pi here is just a number that we don't care about. The length of the string we don't care about. It's going to be the same. The only thing that we're varying is the gravity. So we do care about gravity. My point is that this whole thing here is going to be a constant that we don't care about. So let's just give it a new name. Nice and simple. A nice and simple name. K. Okay. So here you've got K times, times 1 over root G. Okay, so here, so remember, if you're told that y is inversely proportional to let's say square root of x, then you can, if you're told this here, you can immediately jump to y equals a certain constant times the square root of x. So here, well, this thing here is very similar to this thing here. Okay, so we are here at the moment. We're going to work. So we are here at the moment. We're going to work backwards and jump to this. We're going to make the reverse statement, if that makes sense. So when you're here, you can actually say, oh, by the way, t is proportional. So t is inversely proportional to the square root of G. Okay, so you can actually make this statement here. So now t is inversely proportional to the square root of G. So yeah, so now looking at this here, suppose you've got a string of length L, whatever it is, and now G here, gravity. G, let's say at the moment gravity is G. Okay, this is capital T for the time it takes to make one swing. Now, so this here is our current. Okay, current. So the current time, well, the minute you're told this, you can jump to T equals a constant times root g. Okay, so currently, so our current situation, the time it takes to make one swing is given by this. So this is current. Now let's look at a new situation where we double the gravity. So now gravity is 2g. So now hang on. So now looking at the new time. So this is going to be a new. Okay, new. Let's change this to old now. Old. So our old times this. Our new time would be this. T equals a certain number over the square root of, well, the square root of 2g. Okay, because gravity in the old situation it was just g, but now in the new situation we doubled the gravity. We wanted to know what would happen to t when we double gravity. So now use that indices property here. AB square root of AB equals this. Now, if you don't understand this, watch the indices section. So now I'm going to use this property on this thing here. Okay. So this would be, hang on, this would be k over root 2 times root g. Okay. So this would be this. And somehow, so don't forget, this is our time for our new, this is a time for our new situation. New. Look at our old one. This is our old one here. I want to, we want to express the new time in terms of the old one, so that we can see how the new time compares to the old time. Okay, so rewrite this new in terms of the old time here. So I'm going to take the well, this thing here, I can rewrite as this. T equals 1 over root 2 times k over root g. You see, our old time is, well, our old time was given by this. Okay, our old time was given by that, k over root g. Okay, k over root g. So you see, this is our old time here. Now our new time is going to be this much times the old time. Okay, so let's work that out on a calculator. So cancel. So hang on, root 2. Let me put it into memory, and then we're going to get 1 divided by that. 1 divided by root 2 equals this, 0.7. Okay, 0.7 times the old time here. This is the old time, k over root g. So you see, when you double gravity, the new time will be 0.7 times the old time. So it's going to get, the time will decrease. So you can imagine this as being like this. 0, 1. This is the old time, and then the new time is like at the similar to the 70% level of the old time. So this is our new here, our new time. This was our old time here. Our old time was here, but now the time has decreased by 30%. So you can visualize it like that. Okay.